Okay, determine the intercepts and the equations of the asymptotes for the given function. And we have a rational function sitting in front of us, f of x, with a linear expression in the numerator and a quadratic expression in the denominator, which is a little bit new. And remember, if the denominator is equal to 0 or can be equal to 0, that of course is going to allow us to find some vertical asymptotes. So before we deal with that, let's see if we can find our intercepts first here, because that's probably the easiest part, a good way to get some momentum. So our y-intercept involves literally no work. We sub in x equals 0, so we simply have to evaluate this function at 0. And of course we get 0 plus 2 in the numerator, and 0 squared plus 0 minus 6 in the denominator. And that gives us 2 over minus 6, or negative 1/3. And as always in IB, we should probably state that as a set of coordinates, even though it doesn't really state the difference here. So anyway, when x is 0, we would expect our y value to be negative 1/3 for this function. Now our x-intercept, or the root of this function, is a little more involved, but we have to set our y equal to 0. So we replace f of x, which remember is of course y, with 0, and we have to solve this equation, x plus 2 on the top, and this quadratic on the bottom. Now incidentally, it doesn't really matter in this situation, but I'm going to factor that bottom just to make sure we don't get tricked, because sometimes you can reduce these expressions down, but this one doesn't, because if I factor x squared plus x minus 6, we get x plus 3 multiplied by x minus 2. So that's close, but close isn't good enough. If that had have matched the numerator, then we could have crossed that off, and of course we also would have been having some serious problems finding an x-intercept. But that's not the case here. Neither factor in the denominator matches the factor in the top, so all we do now is multiply both sides of this equation by that denominator, and we get the numerator left on the top, on the right hand side, and we simply have 0 on the left hand side. 0 times anything, even that even that denominator is equal to 0, and we get x plus 2 on the top. So multiply both sides by the denominator, 0 stays 0, and you get rid of the denominator on the right hand side, and then it should become fairly obvious that your x-intercept must occur at negative 2, and we'll write that as a set of coordinates. When x is negative 2, this function outputs nothing, or 0. So remember, when you're dealing with a rational function to find your x-intercepts or your roots, you're simply just examining the numerator. So whenever the numerator or the top can be equal to 0, that's where you'll find your x-intercepts. Okay, now let's look for our vertical asymptotes. And since we have a quadratic in the denominator, there's actually 2 vertical asymptotes. And remember, vertical asymptotes occur when the denominator can be equal to 0. So it shouldn't be too surprising that a quadratic quite often can have 2 x values that can make it equal to 0. And in order to see that, we're going to factor the denominator, which is pretty typical when working with a quadratic anywhere. If you can factor it, it gives you some insight. And if we factor x squared plus x minus 6, that'll break down to x plus 3 multiplied by x minus 2. And note, x minus 2 doesn't exactly match the numerator there, and if it did, we could actually reduce this down to just a basic reciprocal function translated, but that's not the case here. We have 2 unique functions on the bottom, so we look at each of them individually. So what would make x plus 3 equal to 0? Well, of course, that's going to be x equals negative 3. So we'll say our vertical asymptote, at least the equation of those vertical asymptotes, is going to be x equals negative 3. And our second one is going to occur an x value that can make x minus 2 equal to 0. And of course, that's x equal to plus 2. So please be aware, sometimes students get confused the difference between an equation and a domain restriction. We are listing equations here for 2 vertical asymptotes. Of course, those equations, when typed into graphing software, will produce 2 vertical lines. And if we're interested in stating our domain restrictions, then we have to use a not equal symbol, because of course domain restrictions are using those same two values, but we're listing off these two x values since we can't input them into this function, or we'll get division by 0. And when we write them this way, they're referred to as domain restrictions. So please don't include a not equal symbol when you're giving me the equation of your vertical asymptotes, but do include a not equal symbol if you're actually listing your domain. So there are two vertical asymptotes for this function. Okay, so we have the equations of our vertical asymptotes, so now we have to look for our horizontal asymptote. Of course, there's only one of those. And what's not immediately obvious is, where is our horizontal asymptote? So keep in mind, typically you'd be looking at the graph to determine where your horizontal asymptotes are, I guess in a first introduction to this type of a function. But once we see the graph, which is located here, you can realize that your horizontal asymptote is a familiar item. It's your x-axis. So it's just like our basic reciprocal function is the same horizontal asymptote. So the equation of that will be y equals 0. And if you're wondering how you would find that without looking at the graph, well, you take a ratio of your highest power of x that's in the bottom and the top. Now, of course, we have different degrees or different powers of x top and bottom, but what's probably obvious here is we don't have any x squares. So if we think of this strangely as 0x squared plus 1x plus 2, then we can start to go back to our little shortcut. If you stack up 0 and 1 as the coefficients of the x squared terms, which remember are the highest power terms, you can figure out your horizontal asymptote here is y equals 0, or the x-axis. Now another way of deciphering that is that if you have a higher degree in the bottom, or a higher power of x, then your horizontal asymptote is always the x-axis every single time. So that's good to know as well. And keep in mind, typically in this situation, your graph is going to be nearby, and that will help you see where your horizontal asymptote is. Okay, now we just have to evaluate three limits. And the first one, x approaches negative infinity. So what is the limit of this function as x approaches negative infinity? And all that means is if x goes far, far left, what happens to our function values or our y values? And we can see that they're getting closer and closer and closer to the x-axis. So of course the y values are getting closer and closer to 0. So we can say the limit of this function as x approaches negative infinity equals 0. And that, of course, is also our horizontal asymptote. Okay, and the next limit. The limit as x approaches negative 3 from the right. Now, this limit, of course, involves the vertical asymptote at x equals negative 3. And remember that plus means x is approaching negative 3 from the right. So if we approach if x approaches negative 3 from the right, we're on this side of our vertical asymptote, and we can see the closer x gets to negative 3 from the right hand side, the bigger and bigger those y values become. So it looks like we're saying this limit is equal to something here, but really what this notation means is as x gets closer to negative 3 from the right, this function gets bigger and bigger and bigger and is unbounded. So we can just say the limit equals positive infinity, but really what we're doing here is just describing the behavior of this function near its asymptote. So we haven't gotten into too much detail on limits, but in order for a limit to be equal to something, it has to be a number. It has to be a real number, and plus and minus infinity aren't real numbers. Okay, so now on to the last limit, which is very similar to the one we just looked at. Of course, it's involving the other vertical asymptote over at x equals plus 2, and this time x is approaching 2 from the left-hand side. So as x gets close to 2 from the left, this function, of course, is going off our graph paper. down below, and of course that's to the left of that vertical asymptote. So all those y values are getting smaller and smaller and smaller. So we can say that this limit equals, be careful using that wording, but we write that it's equal to negative infinity, but really what we're saying that if x gets close to 2 from the left, the closer it gets to 2 from the left, the smaller these the function values become. So we really only have one limit that we've technically evaluated, and that is the first one, because a limit has to be equal to a number in order for it to be in order for it to exist, in order for us to technically evaluate it. And the second and third limits are still legitimate. Of course, it's a common way to write those limits, but it's just simply just describing the behavior of the function near its two vertical asymptotes. Okay, so there we have it. We looked at a more complicated rational function. We looked at the process of finding intercepts, and also looked at evaluating a couple of limits.